Okay, in this video we are going to prove a relationship between the incident matrix of a graph and the cycle matrix of a graph. So the statement reads as follows. Okay, if G is a graph without self loop with incident matrix A and cycle matrix B, so whose columns are arranged using the same order of edges. So we know incident matrix for an incident matrix the columns are indexed by edges, and for a cycle matrix also the columns are indexed by edges. Okay, so assume that this A and B are arranged in such a way that the columns of A and B are in the same order. Okay, then the conclusion is then every row of B, okay, of this cycle matrix is orthogonal to every row of A. So orthogonal means, okay, if we take this matrix product A B transpose, or maybe the other way B A transpose, then we will get a matrix that contains only of zeros, modulo 2. Okay, where A superscript T and B superscript T are the transposes of A and B respectively. Okay, so we know that two vectors are orthogonal if their inner product or dot product is equal to 0. Okay, and that's what this statement says. Okay, the rows of B, okay, you can consider rows of B as a vector, and similarly rows of A can also be considered as a vector. Okay, so if we take the inner product of the first row and the first column of B transpose, which is equal to the first row of B, okay, then if we get 0, then that says, okay, those two rows are orthogonal to each other. Okay, and that's what this statement says. So let me read the statement once more. If G is a graph without self loops with incident matrix A and cycle matrix B, whose columns are arranged using the same order of edges, then every row of B is orthogonal to every row of A. Okay, that is A B transpose, okay, which is, it can be also stated something like this, B A transpose, okay, and that is going to be equal to S whole zero matrix. Okay, so before proving this theorem, okay, let's go through one example. So let's consider this graph G. Okay, and here we can see that this graph has 5 vertices. Okay, it has 5 vertices and 8 edges, E1. Okay, so this is E1, E1, E2 up to E8, E1, E2, E3, E4, E5, E6, E7, E8. Okay, 8 edges. Okay, so that says the incident matrix of this graph G, it is going to be a 5 by 8 matrix. So okay, sorry, it has 6 vertices, not 5. Okay, 6 vertices, V6 also is there, right? Okay, so that says this matrix will be a 6 by 8 matrix. Okay, so that says, okay, this matrix, it corresponds to the incident matrix of this graph. Okay, so it has 6 rows and 8 columns. Okay, and assume that, okay, these columns are indexed by these edges, E1, E2, E3, E4, E5, E6, E7, E8 in that order. Okay, so and if we look at this particular graph, we can see that there are 1, 2, 3, 4 cycles. Okay, so it has 4 different cycles. Okay, and that says the cycle graph, okay, it will be a 4 by 8 matrix. Okay, so and that matrix here corresponds to this one, but here that is a transpose version. So this is nothing but, okay, B of G transpose, and here okay, the edges will be indexed in this way, E1, E2, E3, E4, E5, E6, E7 and E8. So we can see that if you transpose this, we will get a 4 by 8 matrix, and each rows are ordered in the same way. Okay, so that says the first row or okay, first column of A and first column of B is indexed by E1, second column of A and second column of B is indexed by E2 and so forth. Okay. So we can see that if we take the incident matrix of this graph, you get this matrix, and if you take the cycle matrix and take the transpose, you get this one. Okay, so let's look at one or two entries here. For example, okay, this corresponds to the first column times first row times first column. So we can see that if you do that, you get 0. Okay, so you can also verify for the second entry here. So let's look at this entry. Okay, that is 1/3 entry. So that corresponds to the product of, or the inner product of this vector with this vector. Okay, so that is like 0 0 0 times 0 0 times 0 0 times 0, okay, 1 times 1, okay, then 0 times 0, 1 times 1, okay, 0 times 1 and 0 times 0. So we get 1 plus 1. Okay, so we get 2 there. And similarly, you can also see that if you take the inner product of this vector with this one, okay, again you will get, okay, this 1 2 3 4 is there. Okay, 1 2 3 4, so we will get a 1 there and 6 6. Okay, so we get 1 plus 1, which is equal to 2. And if you do the multiplication, okay, you will get a vector which looks something like this. Okay, and that is going to be, okay, so here this is a 6 by 8 matrix and this is a 8 by 4 matrix. Okay, so we can very easily see that, okay, the order of this matrix is 6 by 4. So that is going to be a 6 by 4 matrix. Okay, so you will get a 6 by 4 matrix whose entries will be something like this. And here if you take this modulo 2, okay, you will get a whole 0 matrix. So okay, 2 mod 2 is 0, 2 mod 2 is 0, so you will get a 6 by 4 matrix where all the entries is equal to 0. Okay, so that says the inner product of this vector with this vector is 0, the inner product of this with this is 0, okay, the inner product of this with this is 0. So in effect what we are doing is we are taking the inner product of the first row of the incident matrix with the first row of the circuit matrix. So here this matrix is the transpose of that. So if you take the transpose of this, you get this as the first row of the cycle matrix. Okay, so we are taking the inner product of first row of the incident matrix with the first row of the circuit matrix, first row with the second, and so forth. Okay, so since everything is 0, that says every row of the incident matrix is orthogonal to every row of the cycle matrix. Okay, so we saw that this statement holds for this graph. Okay, so let's go and prove the statement. Okay, so let's prove this one. Okay, so let D be a graph without self loops with incident matrix A and cycle matrix B. Okay, so we are going to prove that AB transpose is equal to 0 modulo 2. Okay, so let Zj denotes the edge set corresponding to the cycle Cj. Okay, so Zj denotes the edge set corresponding to the cycle Cj. For example, if you look at this particular graph, okay, so let's consider one cycle. So suppose that Cj is equal to this cycle, say V2 E5, okay, V2 E5, okay, V2, E5, V4, E3, V5, E7, P2. Okay, so consider this cycle, and here this Zj denotes the edge set corresponding to the cycle Cj. So here Zj K2 will be equal to, okay, this set E5, E3, E7, E5, E3, E7. Okay, all the edges in that cycle. Okay, so let Zj denote the edge set corresponding to the cycle Cj. Okay, so we know that in our graph G, for if we consider any vertex, for any vertex Vj, and for any cycle, so if we consider any vertex Vj and any cycle say Cj, okay, so I think I will use a different index here. Okay, so okay, let me call this Vi. Okay, so in our graph G, for any vertex Vi and for any cycle Cj, either, okay, this vertex Vi belongs to Cj or Vi does not belong to Cj. For example, if you look at this particular example, we can see that, okay, V2 belongs to Cj, V4 belongs to Cj, whereas V3 does not belong to Cj, V1 does not belong to Cj. Okay, so that is true for any vertex and any cycle in the graph. Okay, so so in our graph G, for any vertex Vj and for any cycle Cj, either this Vi, it belongs to that cycle Cj, or it does not, Vi, it does not belong to Cj. So that is true for any vertex and any cycle. Okay, so that must hold anyway. That is very easy to see. Okay, so here we can see that if Vi does not belong to Cj, then there is no edge of Zj which is incident on Vi. Okay, and that's how this Zi is chosen. Okay, so we can very easily see that if Vi does not belong to Cj, okay, in that case we can see that there is no edge of Zj which is incident on Vi. Okay, so that's very easy to see anyway. So if Vi does not belong to Cj, then there is no there is no edge of Zj which is which is incident on Vij. And also we can see that if Vi does belong to a cycle Cj, then there is two edges, okay, exactly two edges of Zj which are incident on Vi. Okay, because if you consider a particular cycle, so let me write down and through that I will explain. So that says if Vi belongs to Cj, okay, then there are exactly two edges of Zj, okay, which are incident on Vi. Okay, because we are dealing with a cycle. For example, if you look at this particular cycle, here we can see that this V2, okay, the V2 is incident on two edges, okay, this V5 and E7. Okay, so V2 is incident on E5 and E7, okay, and E5 and E7 it belongs to E5, E3, E5, E3, okay. E5 and E7 belongs to Zj. Similarly, you can also see that V4 it is incident on E5 and E3, and E5 and E3 it do belongs to Zj. Okay, so that's what I said here. If Vi belongs to Cj, then there are exactly two. That's very important. Two edges of Zj which are incident on Vi. And again, if Vi does not belong to Cj, then there is no edge of Zj which is incident on Vi. So we can very easily see those two statements. Okay, now what we are going to do is we are going to consider a B transpose and see what is going to happen. Okay, now so consider the ith row of A and jth row of B. Okay, so we can see that by the property of transpose, okay, the jth row of B is the jth column of B transpose. Okay, so consider the ith row of A and the jth row of B, and the jth row of B is nothing but, so which is jth column, okay, which is going to be the jth column of B transpose. Okay, so jth column will become the jth row of B transpose. So consider the ith row of A and jth row of B. Okay, so jth row of B will be equal to the jth column of B transpose. Okay, and since the edges are arranged in the same order, the rth entries in these rows are both non-zero if and only if a particular edge ER is incident on the ith vertex Vi and also on the jth cycle. Okay, okay, let me write down, then after that I will explain. Okay, so anyway, we started with something like this, right? The columns are arranged using the same ordering of the edges. So since the edges are arranged in the same order, the rth entries in these rows okay, so there is only one entry. The rth entry in these rows are both non-zero okay, if and only if okay, the edge ER is incident on the ith vertex. Okay, so here we are dealing with this thing, the ith row and jth, okay, ith row and jth row of B, and okay, in that row we are considering the rth entry. Okay, so anyway, it follows from the rth entry, it follows from, okay, these are both non-zero. Non-zero in this case it is equal to 1 because it is a 0-1 matrix. So if and only if the edge ER is incident on the ith vertex Vi and is also in the jth cycle. Okay, Cj. So this is how we define incident matrices and cycle matrices. So this follows from the definition. Okay, so you consider the ith row of A and jth row of B. Okay, since the edges are arranged in the same order, the rth entry in these rows are both non-zero. Okay, if and only this edge ER is incident on the ith vertex Vi and is also in the jth cycle Cj. Okay, so that follows from the definition of incident matrices and cycle incident matrix and the cycle matrix. Okay, next what we are going to do is we are looking at the ith component of okay, this product AB transpose. Okay, and we are going to, if we are able to show that entry is equal to 0, so okay, this I and j are chosen to be arbitrary I and j. So that is true for, that will be true for any I and j. Okay, so let's consider this product AB transpose, and let's look at the ijth entry of this product and see what is going to happen. So by the multiplication of matrices, so there will be an R, okay, where okay, we consider the ith row and okay, we consider the ith row and every element that goes from here or goes through all the elements, okay, in that row. So it will be like this matrix, and consider the rth element and sum over all R times, okay, B. So here we are dealing with B transpose, so this will be like JR, okay, and so this is nothing but sum over all R. By definition, this is nothing but A IR times B J R. Okay, so let's so what we are going to do is we are going to consider different cases, and those different cases will give different values of these two entries, and let's see what is going to happen. Okay, so let's consider an arbitrary edge. Okay, so that says for each edge ER of G in the graph G, we have the following, we will have 4 cases, and let's go through those 4 cases and see what is going to happen, okay, with this summation. Okay, so for each ER of G, we have the following 4 cases. Okay, so case 1, so we are considering an edge here, right, ER of J, an arbitrary edge. Okay, so maybe something like this ER, okay, case 1 will be like this edge ER is incident on Vi and ER does not belong to cycle Cj. Okay, so in that case we can see that okay, the situation is something like this. We have this edge ER, okay, that is incident on Vi, okay, but it does not belong to cycle Cj. Okay, the cycle Cj will be somewhere outside this thing. Okay, this edge, it does not belong to that, right, something like that. Okay, doesn't mean okay. So if this is the case, then we can very easily see that here A of IR is equal to 1 by the definition of the incident matrix of a graph. Okay, since ER is incident on Vi and BJR, okay, since this edge, it does not belong to the cycle Cj, okay, BJR is equal to 0. So that says this product will be equal to 0. Okay, so let's consider the other cases. Other cases is going to be like ER is not incident and ER belongs to this thing and so forth. Okay, so let's go through those 4 possibilities. So case 2, so that ER is not incident on the vertex VI and say that edge ER it belongs to cycle Cj. So if this is the case, okay, so following this particular argument kind of thing, we can see that okay, in this case ER it does not incident on this one, so that says okay, here we can very easily see that IR equal to 0 by the definition of incident matrix, and since ER belongs to the cycle Cj, we have B JR is equal to 1. So we can see that product, okay, this product in that case is also equal to 0. Okay, so case 3. So if ER is not incident on BI and ER does not belong to the cycle Cj. Okay, here in that case we can see that okay, in this case both AR equal to 0 and B JR equal to 0. So the product is again 0. So this product is going to be equal to 0. And let's go and consider the fourth case. So in that case ER do belongs to a cycle, okay, and also it is incident on VI. So case 4. Okay, there GR is incident on VI and ER does belongs to cycle Cj. Okay, so in this case okay, so in the other three cases we have this product is equal to 0, right? Okay, so let me write down that also. Okay, all these three cases, all these cases imply that the ith vertex okay, the ith vertex is not in the jth cycle Cj, and we have okay, so all these cases imply that the ith vertex Vi okay, is not in the jth cycle Cj, okay, and therefore we have AB transpose the ijth entry of this is equal to 0 modulo 2. So if this is the case, then we have this thing. Okay, and here we are going to consider the last case. Then last case is ER is incident on VI, okay, and ER belongs to cycle Cj. Okay, and in this case we can see that okay, if okay, so since this ER belongs to a cycle, okay, ER is incident on exactly okay, 2 vertices. Okay, and not only that, the situation will be like this. Since this VI, in this case this VI do belongs to cycle Cj, right, because ER is incident on VI and this ER belongs to cycle Cj. So that says Vi it belongs to cycle Cj, and that says this Vi is incident on okay, one more vertex other than this ER. Okay, so here we can very easily see that we have exactly two edges. Okay, let's call that edges. So one edge will be ER, right? Okay, ER, and okay, there will be one more edge, ET, incident on VI. Okay, because we have the situation something like this. Okay, anyway, this vertex VI, it is incident on ER. That's our assumption. Okay, and okay, since this is a part of a cycle, okay, that says there will be one more edge that is incident on VI, and we call that one ET. Okay, and okay, these all things belongs to the cycle Cj. So the situation is something like this. So that says we have exactly two edges incident on Vi. Okay, so we can see that a IR is equal to 1 because this edge. So okay, this is not a vertex, this is edge ER. Okay, so since this edge ER is incident on Vi, we have AIR equal to 1, and also AIT. Since this edge is incident on Vi, we have AIT is equal to 1. Okay, and similarly, okay, if you look at this particular cycle, both these edges ER and ET, it belongs to this cycle. Okay, and that says B of JR. Okay, B of JR is equal to 1, and similarly B of JT. Okay, B of JT is equal to 1. So therefore that says if you consider this product AB transpose and look at the ijth entry, so we saw that is nothing but the summation over all R AIR B JR. Okay, so only okay, these entries survive, everything else will be 0. So this will be like 1 plus 1, okay, which is equal to 2. Okay, and that is equal to 0 modulo 2. Okay, and therefore we have A, B. Okay, so this is for arbitrary indices I and j. So this is true for everything. So this will be like AB transpose is a 0 matrix. Okay, and the size or the order of this matrix is like the number of vertices and the number of edges. Okay, it doesn't matter. Anyway, we have this particular thing. We have a 0 matrix. Okay, 0 matrix of appropriate order. Okay, and that's what we want to prove, and that says the rows of A is orthogonal to rows of B. Okay, and that's what we are trying to prove, right? So that says if G is a graph without self loop with incident matrix A and a cycle matrix B whose columns are arranged using the same order of edges, then every row of B is orthogonal to every row of A, or other way also. Okay, is equal to 0. So that said, okay, we have this relationship between the incident matrix and the cycle matrix.